All right, let's take a look at section 16.5, which will cover curl and divergence. So a few more learning objectives this time. First, we'll define what the curl and the divergence are. Then we'll calculate both of those things using some illustrations and some formulas. We can kind of get an idea of what the curl and divergence actually mean. And then we'll try and relate the two together. But first, let's talk about everything that's on this slide. So from back when we were first starting off with derivatives in vector areas, we defined the gradient operator, which is this upside down triangle. And we said that that gradient operator would be the partial derivative in each of our variables. So in 3 dimensions, it can be x, y, and z. So when we took the gradient of a function, we would just take the partial derivatives of each of x, y, and z and set them up in a vector. So when we did just the gradient, we were plugging in a scalar function or taking the gradient of a scalar function, and our resulting output was a vector, or probably a vector field. Now, with the two new things that we're going to add in, the curl and the divergence, they are both going to be derivatives in some sense. And they're going to use the gradient operator, just like the gradient did back from several sections ago. But the main difference is that the curl and the divergence will operate on vector fields or vector functions rather than on a scalar function. So the curl is going to be defined as the cross product of the gradient operator and some vector field or vector function, while the divergence will be defined as the dot product of that gradient operator and some vector function. So when we take the curl, our input is a vector function and the output is another vector function. But with the divergence, our input will be a vector function, but the output then will be a scalar, since the dot product of 2 vectors is a scalar, but the cross product is another vector. So keeping these in mind might be a little helpful as we're trying to differentiate between these 3 different uses of the gradient operator. So starting off with defining what the curl is. So just as a reminder, we defined what the gradient operator was. It's the partial derivative in each of x, y, and z if we happen to be in 3 space. But the curl is going to be some kind of a measure of how a vector field curls around a point. So I've sketched out a few diagrams. Maybe let's start with figure 1, which is from the textbook. And it shows the curl as it relates to some vector field. So the blue portion in figure 1, the textbook drawing, that blue portion is our actual vector field, with the magenta vector being drawn out is the curl at that point. So the curl will be represented by a vector, and it should point perpendicular to the sort of plane or surface that's created by the vector field around a point. So if we use that to then talk about the diagrams I've provided, up at the top we have a green vector field where all of our arrows are curling counterclockwise around that point. And we'll say that in that case, if our vectors all curl counterclockwise, we have a positive curl. And in that case, the curl should point out of the plane. So in each of the diagrams that I'm looking at, we're just going to focus on some vector fields that are only in the xy plane, so that way we can have our curl point in the z direction. So as long as we're curling counterclockwise around a point, then that curl should point in the positive z direction. So it's pointing out of the plane. If we look instead at the red diagram over to the left, we have those vectors, that vector field is curling clockwise around the point, which we'll say that the curl in that case would be negative, so it would point into the plane, point in the negative z direction. And finally, in the lower right, where our vector field isn't curling at all around the point, it's just passing straight through it, I will say in that case that the curl would be 0. So if there's no curl, if there's no bending or swirling or curving to the vector field around our point, then the curl should come out to 0. And keep in mind that in these diagrams, the thing being drawn is not the curl at the point, but rather the vector field near that point. So the green arrows, the red arrows, the blue arrows, those are all the vector field, not the curl itself. And to relate the curl itself to the vector field, that's where, again, you'll want to look at figure 1, which is the diagram out of the textbook, which shows a vector field in blue, and then the curl is a single vector that points out or in from that point. So there's a fun definition. Let's look at actually calculating this thing. So we said on the previous slide that the curl of f is going to be the cross product of the gradient operator and the vector field. And we'll say, just for some amount of terminology, that if the curl is 0 at a point, then that means that the field is irrotational at that point. It doesn't have a lot of rotation going on if the curl is 0. So we said that the curl is going to be the cross product of the gradient operator with our vector field. So it's the determinant of that matrix that I drew in where all the partial derivatives are listed and the elements of our vector field, P, Q, and R. And then also I want to talk about handy shorthand for remembering sort of the order of the way that this curl works. Since if we just look at the curl, it's the z element partial with y minus the y element partial with z, and then the x element partial with z minus the z element partial with y. Finally, the y element partial with x minus the x element partial with y. There's a lot going on there, and so one of the things that I use to kind of help remember quickly the order that this thing should go in is that if I have the elements of that vector field written out as p, q, and r, and I've got my partial derivatives, x, y, and z, and I'll just write out that sequence and repeat it at least once. So my elements go PQR, and my partial derivatives, x, y, z, x, y, z. As I move through the curl, those elements that are p, q, and r are going to go backwards in alphabetical order, while all of the partial derivatives will go forward in alphabetical order. So if we just read our way through that curl, we go RQP, RQP, it's supposed to be the magenta one, RQP, RQP, as we read our way through, so in reverse alphabetical order, while the partial derivatives go forward in alphabetical order. So Y, Z, X, Y. And we've got some letters that repeat, but that's okay. Another sort of important element to note about the curl is that each position in the final result of the curl does not have any element from its original position. So in the x coordinate of our curl, we have nothing to do with p nor anything with a partial derivative of x. It's all q, r, and y, and z. We can repeat that for the y coordinate and for the z coordinate, but we'll see that y is absent from the y coordinate and z is absent from the z coordinate. Just as far as their partials go, each of p, q, and r are all functions of x, y, and z. So there could be elements of x, y, and z within p, q, and r, but as far as the specific elements that we got from the field, p is not in the first position, q is not in the second position, and r is not in the third position. But all right, let's then talk about the divergence. So if the curl is a measure of how the vector field is going to curl around each point within the vector field, the divergence is going to kind of do the opposite. Instead of moving around the point, we want to be talking about moving in or out of the point. So we'll say that the divergence at a point is going to be positive if the vector field points away from the point. So if we're pointing out of the point, if our vector field goes out from a point, that'll be a positive divergence. If the vector field goes into a point, we'll call that a negative divergence. And if the elements going out are exactly equal to the elements going in, that'll make the divergence equal to 0 at that point. So we can have some mixed in and out vectors at a given point. And as long as there's more out than there is in, that'll be a positive divergence. And if there's more in than there is out, that'll be a negative divergence. So as I said a little while ago, the divergence will be the dot product of that gradient operator and some vector field. And for another piece of notation, we'll say that a field is incompressible at a point if the divergence is equal to 0. And then over to the left, we just have a definition of that divergence, but dot product is relatively easy. It's just each element of the field taken with the correct partial derivative and then added up. So, enough of me just talking, let's actually look at an example. So, given some vector field f, compute the curl and the divergence. So here we've got the curl of f, which is some field, and what that should end up looking like, if I can apply that shorthand memory device that I talked about moments ago, in the first position of the curl, that's where P was. So P will be absent. I'm going to move backwards from P. Backwards from P means I'll have R, then minus Q. So as long as I'm going backwards in that cycle, R, then Q. Into the second position, which is where Q used to be, I'll want to move backwards from Q. So I'll have P and then R. The third position, I'm going to move backwards from R, which means Q, then P. And hopefully I left myself enough space to also write those partial derivatives in. So if we move back through and do partial derivatives, we'll want to go forward in the alphabetical direction. So in the x position, I don't want any x partial derivatives. So y, then z. In the y position, I don't want any y partial derivatives. And if I move forward from y, I would first get to z and then to x. Since I'm starting at y and moving forward in that cycle that repeats itself, so yzx, yzx. And then finally in the z position, I don't want any z partials, so starting from z and moving forward, I'll get x, then y. Also notice that in that curl, no element of the field f gets its own partial derivative. So I'm going to take the partial of r with respect to x and y, but not with z. I'll take the partial of y with respect to z and x, but not with y. Partial of p with respect to y and z, but not with x. That kind of a fun idea. Hooray for patterns. All right, so let's actually take some derivatives. Starting with the y partial of r. R does not depend on y at all, so it's just going to be 0. Minus, I'll have the q partial with z, so that'll be 3z squared, giving us a total of 6xyz squared. Next, move into the second piece. I need the partial of p with respect to z. That's in purple. And that should give me, again, 3z squared. So 3y squared z squared minus the r partial with respect to x. So that'll just be 2x, meaning 6x z squared. And then I'll move down a line just so that I can fit all this together. Lastly, we want the q partial with x. So 2yz cubed minus the p partial y. So 2yz cubed. And then we'll simplify that a little bit. Looks like negative 6xyz squared. And the x component. That y component, I don't think simplified much at all. Did it? Nope. So we'll just have to write that out as is. 3y squared z squared minus 6x z squared. But the final element, 2yz cubed minus yz cubed, is 0. So that came out kind of nice. At least the last element did. And next, I will compute the divergence of f, which will just be each partial with respect to the element that it's in. So the divergence of f, let's actually write it up here because I think I'll need a little bit more space. That p partial x is just 0 since p does not depend on x. Let's just put those colors back in. Next, we've got y partial, or q partial y. So that'll be 2xz cubed. And finally, I want z, or r partial z, which looks like it's 6x squared z. Right, and there's not a lot of simplification to be done there. I can just rewrite it without the 0 piece. 2xz cubed plus 6x squared z. All right, let's take a look at example 2. Or we're just going to use an image to make some estimations about the divergence and the curl. So first piece, estimate the divergence at the point 3 pi over 2 comma pi, and then the second part will be estimating the curl at that same point. So I've gone ahead and marked that in red in the middle of that vector field. That's the point that we're looking at. And we can see at that point, we have the arrows are all kind of moving in a counterclockwise direction around the point, but none of those arrows are actually pointing into or out of the point. So because nothing's pointing in or out, or roughly speaking, all of the in is equal to all of the out, the divergence at that point should be 0. Since again, the divergence is just a measure of what's going into the point versus what's going out of the point, or rather what's coming out of the point versus what's going into the point, since things that are coming out will be considered positive and things going in will be negative when the divergence is concerned. Next, we'll take a look at the curl around that point. And since this whole field exists in the xy plane, if we take the curl at any point in this plane, we know that the curl should be normal to the vector field at whatever point. So it should point perpendicular to whatever plane the vector field is in at the point in question. So our curl should point in the z direction, since that would be normal to the xy plane. So we'll say that this curl, which we know is a vector, as opposed to the divergence, which was a scalar, will point solely in the z direction. So both the x and the y elements should be 0. And then we just need to decide if that z component should be positive or negative. So again, if we look at that vector field, those are all swirling in the counterclockwise direction. So we should have a positive z element to our curl vector. If we were to actually calculate these two pieces, I believe we get that the divergence of f is 0, while the curl of f is the vector 0, 0, 2. But that's if we were to actually calculate it. All we wanted to do was estimate based on the picture. And that's probably good enough, at least for an estimation. All right, next, let's relate the curl to conservative vector functions. So assuming that we have some vector function or some vector field f in R3, and its component functions have continuous partial derivatives, then we can say that the curl of that vector field is going to be 0 if and only if that vector field itself is a conservative vector field. So, quick reminder of what a conservative vector field is. If our vector field is conservative, that means that there is some potential function, little f, where that little f is a scalar function into our capital F, which is a vector field, and our vector field is the gradient of that potential function. So that's that first line written out. So our vector field capital F is equal to the gradient of a scalar function little f. So it's the elements of capital F are just the partial derivatives of f with respect to x, y, and z. Then we can compute the curl of that vector field, which is the curl of the gradient of our potential function f. And then that ends up looking like the following. Or if we just look at that first element, we have the second order partial of our potential function little f, first with z, then with y, minus, same thing, but first with y, then with z. And we had a theorem from a few sections ago, Claire-Waugh's theorem, I believe, that says that as long as we have a nice enough function, it doesn't matter what order we take our partial derivatives in, it should end up being the same. Meaning that if I do z then y, that's the same as doing y then z. So in each of those coordinate positions, I end up getting a second order partial minus itself. So it all comes out to 0. So that's proving only one of the directions. Proving the other direction is considerably more difficult, and it'll require Stokes's theorem, which we'll get to in a couple sections. But let's relate the curl and the divergence together one last time. This time, again, say we've got, a nice vector field and it's got continuous second order partial derivatives. Then if we take the divergence of the curl, we get 0. One thing to note between the last two pieces, when we took the curl of our gradient vector field, we got the vector value 0, which is just the vector 0, 0, 0, as opposed to the scalar value 0, which is, somewhat semantic, but just thought I'd point it out. So in the previous result, we had the vector 0, whereas in this case, we're taking the divergence of the curl. So the outermost thing that we're doing is the divergence, meaning we actually get a scalar result. So we should just get the number 0 when we do the divergence of the curl. But if we just put up the math involved in taking the divergence of the curl, we're just going to take the partial derivatives of each of the 3 components of the curl, and we should hopefully see if we match up the colors that for every positive term we have exactly a negative term, just with the order of the partial derivatives swapped. But by that same theorem, we could say that, for example, p sub zy is equal to p sub yz. So when we're taking the difference there, it just comes out to 0. Since the order we take those partial derivatives in should not matter as long as we have a nice enough function. So as one last example, we want to ask the question, does there exist a vector field, capital F, such that the curl of F is equal to the function provided? So if we wanted to check to see if that field exists, this is pretty similar to the way that we would check to see if a potential function could exist for a conservative vector field, where in that case, we just took some partial derivatives, check to see if they're equal. In this case, we're going to take the divergence of the curl and see if it comes out to 0. If the divergence is 0, we have a vector, there is some potential vector field. And if the divergence is not 0, then that means that no, there is no potential vector field whose curl is the function provided. So let's just go ahead and do that. Divergence of the curl of F is, I want to take P's partial with X. So let's do P partial X plus, we'll do Q partial Y plus R partial Z. Where our P is XZ, so that partial derivative is Z plus Q is XYZ, so Q partial Y is going to be XZ. Plus R partial Z, R is negative Y squared, so the partial of that with respect to Z is 0. We should hopefully notice that if we add all that up, we decidedly do not get 0, since we get Z plus XZ, or maybe Z times X plus 1 if you felt like factoring. Either way, the divergence of that curl did not come out to 0, which means that we do not have some vector field F such that the curl is equal to the function provided.